All right, so that's basically general motion. Um, Next is basically a special case of general motion, which is projectile motion. So projectile motion is essentially anything that is acting under Earth's gravity or acceleration due to gravity. So there's some key like point that's important in understanding projectile motion. So if we just consider this drawing right here, where we have a cannon, it's shooting a cannonball horizontally. And let's just assume for this that gravity is acting downwards in this direction. So if we just show the green ball going to point B would be the actual path that the ball follows. And then each of those lines just represents a snapshot in time, and the intervals in time are equal. So let's just write delta t, delta t, delta t, t, delta t. So each of these times are equal. So in the horizontal direction, which is perpendicular to the direction acceleration due to gravity, the velocity is constant. So in this horizontal direction, our velocity is constant. It's not changing. There's no acceleration term or zero. So it doesn't matter how far something drops. I guess the height of the projectile falling, the component of the velocity in the horizontal direction is always going to be constant. And then because we have a constant acceleration g in the vertical direction for the same time increments, the distance that the projectile moves over that time increment is going to be continually increasing and increasing and increasing. And that increase is parabolic. So the vertical velocity changes due to gravity. So those are the main points about projectile motion. Velocity in the horizontal direction is constant, and velocity in the vertical direction changes due to gravity. So if we were to draw just a particle along a path, which is undergoing projectile motion just like we did before, we can do everything the same as our previous problems, except now we just have a constant acceleration term, and we know its component. So we have our position vector, and that's pointing to our particle, which has velocity components vx and vy. Its velocity is tangent to the path, although it doesn't really look like it's tangent to the path at that point. And we can write our equations of motion. So since the x component of our acceleration is equal to 0, using our kinematic equations from lecture 1, we can write the position, because we have a constant acceleration case. The position is equal to some initial position, a reference position, x0, plus the initial x velocity times time. And we only care about the initial x velocity because the velocity in the x direction is constant, it's not changing. So we can say the 0x is equal to vx. Write that up here, is equal to v0x. So the x direction is quite easy. We have this one equation. We can use that. If we look at the vertical direction, the y direction, we now have our component ay of our acceleration is equal to minus g, and it is constant. We said before g is equal to 9.81 meters per second squared. So we again use those equations of motion for constant acceleration. We can rewrite the three equations of motion for a projectile as number one, our y component of velocity is equal to our initial y component of velocity minus acceleration due to gravity times time. Our next equation, our y position, is equal to our initial y position plus v0 y times t minus 1/2 acceleration due to gravity times t squared. And then our last equation, equation 3, vy squared is equal to v0 y squared minus 2 times acceleration due to gravity times our change in position y minus y0. So let's do a quick example with some projectile motion. So we have Lionel Messi here. He kicks a ball at an angle of 30 degrees with respect to the ground, and the speed of the ball as it leaves Lionel's foot is 10 meters per second. The question says determine how far the ball travels before hitting the ground. So we have our four equations of motion that we can use, one in the x direction and three in the y direction. Basically, we have to determine the unknown here, which is what will be that x position, how far will the ball travel before hitting the ground. So how far away is point C from point A? So basically we're asked to find xc when ball hits the ground. So how can we do this? What do we need to know in order to solve this? So we have v0x, v0y. We know the acceleration, so it's just gravity. So what is our x component of velocity, our initial velocity?
10 cos 30.
And then we know our y component is 10 sine 30. So using these, if we look back up to our equations, which of these equations do we think might be useful? So if we look at equation 1, we don't really need to find this component of velocity. We don't really care what that is. So let's not use equation 1. If we look at equation 3, we have that Vy again. So maybe not equation 3. So let's try equation 2. We have a position y, which is convenient just by the geometry. It looks like it's going to land at the exact same position in y as when it was kicked. So we know if we use equation 2, this y over here is going to be equal to y0. And then we have no other unknowns except for t. And then if we have that, we solve for t, then we can use that in our equation for our x position. We know our v0x, we know our x0, say is 0. We substitute t in there, then we can solve for that unknown x. So we have two equations, we need to solve t, and then we can solve for x. So let's use that equation for y with the velocity, the initial velocity in the y direction is 10 times sine 30. So if we write that, we know, we can write our equation for y. Y is equal to y0 y0 plus v0 yt minus 1/2 gt squared. So y and y0 is just going to be equal to we'll say y0 is equal to 0. This is also going to be equal to 0 because we're just assuming that this is 0. So we're left with v0 y times time is equal to 1/2 gt squared. And if we do this, we can cancel out one of the t's. And we're left with v0y, so 10 sine 30 is equal to 1/2 times 9.81 times t. And we should get t is equal to 1.019 seconds. So we've got the amount of time. Now all we need to do is figure out after 1.019 seconds, how far has that ball moved in the x direction? So we can write our equation x is equal to x0 plus v0x times time. Let's say x0 is 0, our v0x is 10 times cosine 30, and our time 1.019. Should get our x position is equal to 8.83, write that a bit neater, 8.83 meters. So it's kicked at a velocity of 10 meters per second, an angle of 30 degrees from the ground. It's only going to go 8.83 meters before it hits the ground again. So let's look at an example which is a little bit more complicated. So in this case, we have a cannon shown. It gives us a representation of the inclination of that initial velocity, and it tells us the initial speed is 150 meters per second. So it's asking to determine the range of the cannon shown if it has a muzzle velocity and inclination angle of 150 meters per second, and we'll call the gradient is 3/4. The rise or run of the inclination is 3/4. And then it also asks how long before the cannonball lands at B. So how should we move ahead with this? I always think it's easiest to do the exact same process we did for the first problem. Let's just start with some of the things we know. So we know v0x is equal to, we use similar triangles, the x component would just be 4/5 times 150. And that is meters per second. We know v0y is going to be equal to 3/5 times 150 meters per second. And we know that if y0 is up here, and we can write yb, or y down here, is equal to minus 150. So let's write our equation. Y is equal to y0 plus v0 y times t minus 1/2 gt squared. Minus 150 is equal to 0 plus our y component is 3/5 times 150. What's 3/5 times 150? Let's simplify that. Hopefully you get 90 times t minus 1/2 times 9.81 times t squared. So we only have one unknown. And if we solve for t, so if we solve this equation right here, we have a quadratic equation t and t squared, we should get two values for t. One of them, this is the one we're looking for when the ball lands at point B. The other one is going to be some negative amount of time. So if we go backwards through time or move this path backwards, it would be the time corresponding to when this parabola would cross that ground level axis. So we don't care about that negative time, we only want the positive value. So if we solve this equation and we only look at the positive value, we should get t is equal to 19.89 seconds. So if we use the same process as before, we now have time, we have our initial x component of velocity, so we can write x is equal to x0, which is just going to be 0, plus v0x times time. So we have 4/5 of 150 times time, which is 19.89. And we get x, which is our range. And that range will be equal to 2,387 meters. So the cannon's launched at 150 meters per second at that angle, and it's 150 meters above the ground. The range of that cannon, or the distance it'll travel before hitting the ground, is just about 2,400 meters. Good. So in this problem, we have Phil is chipping onto the green, and he hits his ball with the path that's shown. So he's hitting it with the speed of 80 feet per second at an angle of 45 degrees with respect to the ground. And the ground is at an angle at 10 degrees with respect to the horizontal. How far does Phil's ball get for the first bounce? So basically, what is that distance d when the ball lands at point B? So this time it's convenient if we, since everything's tilted, let's be, I guess, specific about what coordinate frame we're going to choose. So because it's projectile motion and gravity is always acting vertically, it doesn't really make sense to have our coordinate system on an incline with the ground, because if it's on an incline with the ground, then we have acceleration in both x and y directions. So let's keep the same equations we had before. Let's draw our coordinate reference frame. Y is here, and x is horizontal. So we're going to keep y is vertical, x is horizontal. So everything now is going to be with respect to this frame. So we know that b0x is going to be 80 times cosine of the angle between the ball being hit and the ground. So that's 45 plus 10. So that's 55 degrees. V0y is going to be 80 times the sine of 55 degrees. So the other thing we needed to know to solve these problems before is the value. What is that value of y? How can we figure this out? Well, y would just be the vertical rise of the ground at the point that it lands at point D. So we're going to find y as a function. So if we extend this line over here, or I guess this line, this distance y here is going to be d times the sine of the angle of inclination, which is 10 degrees. So if we use our equation, then we want to solve for the time of flight, and then once we know the time of flight, we can figure out, okay, what is the distance traveled in the x direction to reach that, and then at the last point we have to not just figure out x, we need to figure out the distance d. So it's going to be square root of the sum of y squared plus x squared. So let's write our equation. Y is equal to y0 plus b0 y t minus 1/2 g t squared. So we'll set this up. Y now is d sine 10. We'll say y0 is 0. Our b0 in the y direction is 80 sine 55 times t minus 1/2 acceleration due to gravity in feet per second squared is 32.2, maybe t squared. So this is one equation. We have two unknowns still, d and t. So let's look at our motion in the x direction now. If we write down x is equal to x0 plus b0 x t, we'll end up with x is equal to, well, x0 we'll just say is equal to 0 plus 80 cosine 55 times t. And we can write the value of x. If the distance along that plane is d, that means the distance x we can write as d cosine 10. So we have our second equation. So we have two equations, two unknowns. We can substitute equation 2 into equation 1. And then we can solve for that distance. And if we do that, we would get d is equal to 0 or 166 feet. You know, obviously the 166 feet is the meaningful answer, the one that we care about.